So we're doing number 3 now. It says, at what distance would a supernova of absolute magnitude of -20 be as bright as the sun? All right, so we got to look up the apparent magnitude of the sun, and as bright as the moon. And would you expect this supernova to occur that close to us? Okay, so for both situations. All right, so let's work on this problem. All right, for this one, they give us that the absolute magnitude of this supernova is -20. They want to know what the distance is. That's what we're solving for. And you got to look up the apparent magnitude of the sun, which is -26.74. So we use this equation, of course. Distance in parsecs is equal to 10 to the apparent magnitude minus the absolute magnitude plus 5, and then that whole thing divided by 5. All right, so I put the numbers in right here, and let's get my mouse so I can see it. All right, so it's 10 to the -26.7. It's minus a -20, right? So this part right here, minus a negative becomes a positive. Sorry, that's just an underline. All right, and then plus 5, and then the whole thing divided by 5. It turns out to be the distance is equal to 10 to the -0.348, which turns out to be approximately 0.45 parsecs. All right, and so to answer that second part of the question that said, would we expect to see any stars or any supernova this close? I mean, there's not even any stars this close, right? This is, if we multiply this by in 1 parsec, there's 3.26 light years. 3.26 light years. When we do that, we can just keep in mind that the closest star to the sun is Alpha Centauri, and that's a star slightly more, maybe twice the mass of the sun. There's no way that that's going to ever go supernova. All right, so when you do this in light years, you keep in mind Alpha Centauri again is more than 4 light years away. So this turns out to be about maybe 1.5, if I round, 1.5 light years. So there's no stars that close to our sun. So we'd never expect to see a supernova as bright as the sun. Okay, that had an absolute magnitude of -20. All right, now let's try this with the moon. So we got to look up it's the exact same equation. We just have to look up the apparent magnitude of the moon. All right, so I'm assuming they mean the full moon. All right, so I look up the apparent magnitude of the full moon. Remember, we're still dealing with an absolute magnitude of this particular supernova of -20. All right, so this would be very bright. Remember, absolute magnitude is how bright it would look if it was 10 parsecs away. Anyhow, so we use the same equation, and so it's going to be -12.5 plus 20, because it's minus a negative, right? So that becomes plus 5, and then that whole thing divided by 5 turns out to be 10 to the 2.5, which gives us about 316 parsecs. So this is a reasonable distance. It's not super far or anything like that from our sun, but it's certainly going to encompass several massive stars, right? In that you just if you imagine the sun is at the center, and you sweep out a radius of or a distance. Well, I guess we should just use distance. A distance of 316 parsecs in all directions in 3 dimensions. You're going to pick up quite a few. I'm guessing I'm just making this up, probably, I don't know, maybe 100 supernova, possible supernova. All right, so a few. I'm just going to say a few. All right, because this isn't like a great distance from the sun, but there's certainly going to be some stars. Remember, most of the stars are the low mass stars, right? That will never become a supernova. All right, let's move on. All right, so here's number 4. Calculate the orbital speed. So we got to look up that formula. It's very similar to the escape velocity formula, by the way, of matter in an accretion disk just above the surface of a 0.6 solar mass, 0.6 solar masses, and the diameter is 15,000 kilometers. Okay, and of course this is for a white dwarf. All right, so let's work on this problem. All right, so let's see here. Let's see if I can switch this. All right, very nice. And so there's the equation, the orbital speed. So the only difference between the orbital speed and the escape velocity is you'd put a 2 right next to this big G. All right, so they give us the mass is 0.6 times the mass of the sun. So we just multiply 0.6 times 2 times 10 to the 30th, and the R here. So remember, R is the radius, is, let's see, what did they give us? 15,000 kilometers, right? 15,000. Now, I'm going to change it from kilometers to meters, okay? So I would just add 3 more zeros just to make it simple, or you could say times 10 to the third, that's the same. The reason I'm doing that is the mass, the R here has to be in meters. Now remember, this is, they gave the 15,000, which is really 15 million meters, is the diameter. So we have to divide that by 2. Okay, so just keep that in mind. All right, so all right, let's go ahead and do the rest of this problem. All right, so these are the numbers. 0.6 times the mass of our sun turns out to be 1.2 times 10 to the 30th, and then half of 15,000 turns out to be 15 million, right? Because we're in meters, turns out to be 7,500,000. All right, so you take the square root of that, and you get. And remember, you're using big G there, that's the universal gravitational constant, something like 3 point, I don't know, I'm going to round here, 3.3 times 10 to the 6th meters per second. All right, and usually in these kind of things, we compare these velocities to the speed of light. So like if I divide by the speed of light, which is, 3 times 10 to the 8th. So I take this number, divide by 3 times 10 to the 8th meters per second. You get the following, right? So this is 3.3 times 10 to the 6th divided by 3 times 10 to the 8th. It's approximately 0.01 times C. Right, remember, C is this value right here. So it's really approximately 1% the speed of light. All right, so because a lot of times they'll do that, they'll compare a particular speed, especially when they get really close, or they start to get close to the speed of light. We like to compare them to the speed of light. So that's, so you could say that this orbital speed right on this, near the surface of a white dwarf, of this mass and this radius would be something in the accretion disk would be traveling at 1% the speed of light, which is pretty significant. That's a pretty significant speed. All right, let's do the next one. All right, so here's number 7. The Crab Nebula is now 1 parsec in radius. All right, so if it's exploded in 1054, roughly, how fast is it expanding? Assume a constant expansion rate. is that a reasonable assumption? And it certainly is. I mean, it's going to slow down a little bit due to material out there in space, but it's more or less traveled constantly. All right, so here we're setting up problem 7. 1 parsec turns out to be 3.1 times 10 to the 13th kilometers. We take the year 2021, subtract, so this is the year that I did this calculation. 2021 minus 1054 gives us 967 years. So we got to convert that to seconds. All right, so we have to know how many seconds are in 967 years. So you multiply by 365 times 24 times 60 times 60 again, you get roughly 3.05 times 10 to the 10th seconds. All right, so that's the number of seconds the Crab Nebula has been expanding. All right, so just think about the picture that we're using here. So this thing has been expanding outward in all directions, right? And so presently it's the radius. Okay, so the radius of it. So from the center when it started to expand to right here, that radius, so we'll call that right there R, is 1 parsec, or for our purposes we're going to do it at 3.1, well this number right here, 3.1 times 10 to the 13th, 3.1 times 10 to the 13th kilometers, right? And if it's been moving at a constant speed, we're just going to take 3.1 times 10 to the 13th divided by the number of seconds in 967 years, and that will give us the speed. And notice the speed will be in kilometers per second. All right, so let me read. All right, so this is the setup. This is the distance, right? This is the distance for one parsec in kilometers, and this is the time. All right, so I'm going to, hold on, let's see, so 3.1 times 10 to the 13th. I'm just putting this in my calculator right now, divided by answer, which was the number of seconds. So I get a speed of 1016.5 roughly. That's perfectly fine. 0.5 kilometers. That's kilometers per second. All right, so that's how fast the Crab Nebula is expanding. Okay, and so it'll this is assuming that there's nothing slowing it down. All right, very good. So and I think that is it, right? Is that it for yes, that's it for the problems for chapter 21.